So let's continue our derivation of the Boltzmann distribution PR by the so-called method of most probable distribution. We were halfway during the derivation. Hope you remember that we were discussing about maximizing W to make or to find out the most probable distribution set NR, and in order to maximize log of W in place of W, where W was the number of ways in which the set NR can be achieved, we have seen that the maximization should be following two constraint equations given by equation 2a and 2b, which were sum over r nr should be equal to n, and which is 2a, labeled here as 2a in our derivation, and the second constraint equation was that sum over r nr er is equal to E, the total energy that is shared by n members of the ensemble. So without violating these two constraint equations 2a and 2b, the W has to be maximized. And since W is a very large number, we consider maximizing log of W in place of W, which is practically the result is the same. So for W to be the maximum, we have obtained delta of log W is equal to 0. Okay, or the differential of log W should be equal to 0, and delta of log W is given by equation number 4 anyway. And see, from conditions 2a and 2b, the constraint equations 2a and 2b, we have rewritten the expressions 5a as taking delta sum over r delta nr is equal to 0, and sum over r er delta nr is equal to 0. So which are written as 5a and 5b respectively. So this is our maximization that we have to perform now. Now see, let me I think yeah, we have concluded our former session by telling that such a type of maximization can be done with the help of a special technique in mathematics called the Lagrange's method of undetermined multipliers. So when do we use the Lagrange's method of undetermined multipliers? So let's see. So this is just okay, a note for you. So in statistical mechanics, one very often comes across determining the extremum values. You know, extremum value means it can be either a maximum or a minimum, right? So you are very clear about extremization principles in classical mechanics, like the least action principle and all. We have discussed a lot about that one. So we very often want to find out the extremum value of a function of several variables, say x, y, okay, so say that of pressure, okay, temperature, or say that of n, v, t, whatever it is. So of several variables, under the condition, this is something significant, under the condition that there exists some constraints between these variables. Okay, so that is, without violating the existing constraints, some function of several variables has to be extremized. Let me give you a simple example. For example, see, if you go for some okay, common example, say that suppose that we have a function, say a function of two variables, say x and y. So let me say that suppose f of xy, you take any simple functional relationship between x and y. Say that let me take the product function f of xy is equal to xy. Suppose we want to maximize this function, we want to extremize this function with the condition that, without violating the condition that x square plus y square should be equal to say 1, right? Means we have to extremize the function f of xy. This has to be extremized, but see, during the extremization, the function has to still obey, or it should not violate this condition. Okay, whatever way you extremize f of xy, Okay, the condition that x square plus y square should be always equal to 1. So this is not a simple extremization, because you know that during the extremization this constraint equation has to be satisfied. So in such a situation, in such a process of extremization, including some constraint equations, it was Lagrange, okay, a mathematical genius, who suggested a method which is nowadays known as the Lagrange's method of undetermined multipliers, which I have abbreviated as LMUM. This is not an accepted abbreviation, so just call it as Lagrange's method of undetermined multipliers. So what we will be doing in this method is that we will be introducing two constants. You can call it as some now constants for the time being, or two multipliers, two coefficients. So usually the Lagrange's multipliers are usually represented by alpha and beta. So we are going to introduce two multipliers or two coefficients alpha and beta, which is not defined now. Okay, but later depending on the situation, we can identify what is this alpha and what is this beta. Okay, or you can say A and B, whatever it is. So alpha and beta are usually introduced as 2 or 3, whatever, okay, depending on the number of constraint equations. So if there are 2 constraint equations, we have to introduce 2 multipliers. If there are 3 constraint equations, we have to multiply, okay, you have to introduce what, maybe alpha, beta, gamma, likewise it goes on, right? So since we are having 2 constraint equations in our present problem of Boltzmann distribution function, we will be introducing 2 multipliers, say alpha and beta, okay, which are undetermined, whose value is not known now, okay, at present. Now what we'll be doing, we will be multiplying this alpha with the first constraint equation. So alpha, you can say that alpha is say it is multiplied with one of the constraint equation, and beta is multiplied with, or say, the second constraint equation, or you can do the other way. It's not a problem, which is alpha and which is beta. So alpha and beta are multiplied with the constraint equations, and they are after that we'll be defining a new function, and instead of maximizing the original function f of xy, we will be trying to maximize the newly defined function which includes these constraint equations obtained by multiplying with the undetermined multipliers alpha and beta. So this alpha and beta are what is known as what? The Lagrange's undetermined multipliers. And later, say from the problem, you can determine what is the value of alpha and beta depending on the particular problem. So this is the method, and we will see how this particular method helps us to come out of the extremization problem. What we are discussing is the Boltzmann's distribution, and we will be using the same undetermined multiplier method later in our quantum statistics as well. So remember that this method of Lagrange's undetermined multipliers finds its application very often in many of the derivations of statistical mechanics, where the system has to obey certain constraint equations. At the same time, some quantities are to be getting maximized. Okay, so there are several just references, but I find one reference especially useful. That is a book on statistical mechanics by B.B. Lord. It's a very crispy book. Okay, and the method of Lagrange has been given as an appendix there. You can, for details, you can refer to that, but I think mostly it will be enough. When you apply it in 1 or 2 problems, you will be familiar with the technique. Okay, so later. So I think let's now come back to our own problem. So we continue with our extremization problem. So let me just once again write down our results that we have. Okay, so we had from equation number 4, I am writing down equation number 4 time and again. Equation number 4 was actually it was expression for log w, right? Expression for the log w. So which was, let me take it, it was delta of log w, delta of log w. You know, delta means variation in, or differential of log w, which is supposed to be 0. Okay, for w to be maximum. Our aim is to maximize w actually within the constraints. So minus sum over r means sum over all accessible states, 1 plus log of nr, 1 plus log of nr. Okay, then delta nr. Okay, so this was our equation number 4. And also we had rewritten equation number 2a was rewritten as equation 5a. So 2a, from the constraint equation 2a, we have written it as 5a as sum over r delta of nr is equal to 0. So this is from this equation has followed from the constraint equation. What is the constraint equation? Sum over r nr should be equal to capital N. That was the actual equation. Okay, and from 2b we have rewritten it as a 5b. One more condition was obtained, which was what? Which was see, sum over r er delta nr must also be equal to 0. Okay, so I'll be using these three relationships. Okay, so this is the first one. Equation 4 is the condition to be satisfied, and equation 5a and 5b are representing the constraint equation that has to be satisfied along with the extremization of log w. Okay, now yeah, I think before we proceed on, let me tell you what actually is the physical meaning of this this particular constraint equation. So what does mean is sum over r delta nr must be equal to 0. You will understand it clearly. Okay, so what's the meaning? For example, let me consider a simple example will help you to understand that one. Suppose that I am considering two levels. I'm considering, okay, no, it can be a multiple level or many level system. I'm considering two levels. Say that this is level 1 and this is level 2, or state 1 and state 2. You can call it as whatever way. Okay, so this is state 3 and this is state 4. Okay, I'm considering only a non-degenerate level. So states are equivalent to levels. The number will be same. Now suppose that initially that the first state is having at a particular state, say at a particular thing, see this state is having, say that I am taking that I am having there are 5 particles. So there are 5 particles. So n1 is equal to 5. I am taking a toy model. Remember, it is not a statistical model. And say that the second state was having only 2 particles. Okay, or 2 particles are there in the second state. So n2 is equal to what? Say 2, right? And let me say that the other states are empty, right? So what actually it means, okay, if you talk in terms of states, what it can mean is that suppose okay, one of this particle has got, okay, in another distribution, right? Suppose one of the particle is getting shifted to the second level. So what will happen is that the second level will be now having 3 particles. Now the second level is having 3 particles, and see the first level has got only what? 4 particles. So that the total number of particles is what? 5 plus 2 is equal to 7 itself, right? Okay, the total number of particles is not going to change. Only there is a rearrangement. So this is yet another distribution, right? But this distribution, see this particular type of distribution should in no way say that I'm just talking about certainly their energies are different at this particular point of time. I'm trying to explain only this condition. Okay, so I'm ignoring the second condition, which is to be satisfied now. Okay, and you can think about that condition, how both the conditions can be satisfied simultaneously, that you can think of some other examples. Okay, so what will happen here, the condition, what the constraint condition says is that okay, the sum over r delta nr should be equal to 0. Is it not? Sum over r delta nr equal to 0. What does it mean? Let me calculate delta of n1. Delta of n1. What is mean delta of n1? Means the change in n1. So what will be change in n1? It will be the initial value of n1. Okay, sorry, the final value of n1. Let me call it as n1 dash minus the initial value of n1. So what is the final value of n1? N1 now has got reduced to only 4. Because one particle has already transitioned to the second level, right? So it is 4 minus, what was the initial value of n1? Initially it was 5. So it will be 4 minus 5, whose value will be what? Minus 1. Got it? Its value is equal to minus 1. Now let me same manner can you calculate what is delta in n2, delta of the second, the population of the second level. Okay, initially the level was having only how much? 2 particles, and finally the level is having what? Or the state is having 3 particles. So it will be n2 dash, the final number of particles in the second level or second state, minus n2, which will be of course equal to 3 minus 2. Okay, 3 minus 2, I have to take final minus initial to get a change. So that will be equal to what? Plus 1. Have you got it? So it is equal to plus 1. Now what actually is this condition telling? What is this condition demanding? I think I clearly understand. What is that? Okay, for the entire system, if you calculate for the entire system, sum over r delta nr, sum over r delta nr, what is the meaning? Okay, it means that delta of n1 plus delta of n2 plus whatever number of states are there, okay, that should be equal to 0. And can't you see that if in my toy model example, delta of n1 plus delta of n2. So delta of n1 is equal to -1 and delta of n2 is equal to what? +1. So can't you see that those two will be getting added up to give you this big zero? And that is actually the meaning. And I think you can pretty well understand that these constraints just demand that the total number of particles in the system, or the total number of particles in the ensemble, whatever it in a particular, okay, no, just ensemble in a system, okay, that's what conserved, okay. And that is because we have taken that because of the condition that sum over r 2a, okay, nr is equal to what? Capital N, and the capital N should be a constant. So in order to keep capital N a constant, whatever changes that is happening within the levels, of course that would be following this constraint equation, the sum over r delta n r equal to 0. The same manner altogether or simultaneously this particular condition also to be satisfied, okay. That makes things a bit more complicated, right? So not only the number of particles, but the transition, the net transition should be happening in such a way that the total energy sum over r nr er should be equal to E, the total energy that is shared by the members of the ensemble, okay. So I just spent some time to tell you what actually is okay, the physical meaning of this equation. You can think over it more, okay. So that will be helping you maybe when you write down. So I'm going for maximization of this quantity using Lagrange's method of undetermined multipliers, okay. So I'm just continuing with the derivation now by Lagrange's method of undetermined multipliers. I'm writing in short, okay. So we are going to maximize log w, okay. So for that you can say log w has to be maximized, I'm just writing it for getting a beginning. Has to be maximized within the constraints, or without violating the constraints, within the constraints, okay, within the constraints. Now for that, what I'm doing, we will be defining a new function. So for this let's define, see that how simple this method is. It's not complicated. Let's define a new function. We are going to define a new function which incorporates the original function to be maximized as well as the constraint equations, okay. New function, say f, okay. I'm calling that new function as f stands for, you say function, f equal to, so what is this f including? F includes the original function to be maximized. Remember, the method should be understood. The new function will be including the original function which has to be maximized. So I'm writing f is equal to log w. Then what I will be doing, I'll be incorporating the two constraints that has to be satisfied, okay. So this is constraint 1 and this is constraint 2, and both the constraints are also included in the same function. And how do I include the same, okay, constraints here? I'll be introducing two undetermined coefficients, alpha. I'm taking alpha. So this alpha is one of the Lagrange's undetermined multipliers, okay, which is so far unknown to us. Don't worry, okay, it won't affect our okay, calculations. So I'm multiplying alpha with the first constraint, okay, with the first constraint. So what I'm writing, I'm taking alpha into sum over r delta nr, okay. Similarly, I'm putting minus beta into, what is beta? Beta is the second Lagrange's undetermined multipliers, okay. Beta into, what I have to do? I have to multiply with the second constraint, okay, that has to be satisfied. So that is sum over r, what is that? er delta nr. And I am, okay, I know, or okay, we know that this one, okay, so we are defining that this particular thing as equation number, say 6 for us. So this is a new function where we have to, since we are introducing alpha and beta for the first time, we can define it where alpha and beta are the some undetermined multipliers which incorporates constraints into the condition, okay, are the Lagrange's undetermined multipliers, okay. Believing that you know the method, you identify these people, we are just telling that, that's enough, okay. We know the okay, the procedure. Now that is f, we have defined a new function. Now what we are going to do, we have to actually maximize log of w. So instead of that, we are going to maximize f. Instead of maximizing log of w, okay, we are going to maximize f. And maximizing f is equivalent to maximizing log w. Why? Okay, let's check it. That is, I'm taking delta of f, you know, okay, variation in f. or differential of f, you can say, called in the mathematical language, and called as differential in f. So you take differential on the right side also. What will be the differential on the right side? You take the differential of each and every term on the right side. So delta of log w, the first term, right, minus alpha is a constant, it's not going to be affected by taking differentials, minus, you know, when you take this one, sorry, I just committed a mistake here, pardon me. I wrote this one, it has to be just okay, a bit of time, please allow me. So here I have to incorporate only the constraints. Okay, what is the constraint? Sum over r nr is equal to 0. Okay, and what is the second constraint? Sum over r nr er is equal to 0. So I'll be just writing the constraints here, not this equation, okay, 5a and 5b. Instead of 5a and 5b, we'll be writing the constraints 2a and 2b. Okay, automatically the other one will be coming when you take the differential. So just pardon me for that mistake. So what will happen when you take see differential of the second term? Of course, alpha is taken outside, then sum over r delta, instead of r it will be delta nr. So here comes delta nr. So I'm writing delta nr. Okay, similarly, what will be the next thing? Minus beta into sum over r. Okay, of course er is not going to change, right? Because as I mentioned in the previous video, that er is characteristic of the system. There is no any change in er value. Only er into nr will be getting changed. So I can write nr is still variable delta nr. Now this delta f, that must be equal to 0. What is putting this equation equal to 0 means? It means that we are actually maximizing f, whereas we actually wanted to maximize this log w. And you can understand that see, maximizing this f is actually meaningful. Why? Because already you know that from this equation, from equation 5a, what about see, sum over r delta nr? Sum over r delta nr is already equal to 0. So this term is actually equal to 0. And see, sum over r er delta nr is also equal to 0 from this relationship. So this is also equal to 0 actually. So what actually we are doing in this equation? We are putting alpha into a quantity which is already established as 0 and minus beta into a quantity that is already established as what? 0. So actually this is putting delta of log w equal to 0. Okay, which is otherwise delta f is equal to 0. I think I understand that. Now we may be thinking, what is the benefit of doing this? And let's see what is the benefit of doing that one. Okay, so I'm coming back to the derivation thereafter. So now what we are going to do, can we substitute for all these quantities? Delta of log w, we have got delta of log w is equal to this one. This is equation number 4. So I'm substituting delta of log w. It means that delta of log w is minus sum over r. Be very patient, please. Okay, actually it is a bit lengthy derivation as it seems now, but it will be completed within some 5 minutes once you do it in a single stretch after understanding every step what you are doing. So 1 plus log nr, 1 plus log nr, so this is the thing, into delta nr. Of course that delta nr, I am writing equation number 4 here, then minus alpha into, I am repeating the same thing only now, alpha into so minus alpha into sum over r delta nr minus beta into sum over r, okay, er delta nr, which is equal to 0, right? So that is by just substituting equation number 4 in the present equation. Now you can see that there is sum over r, okay, or minus sum over r delta nr. These terms are common for each of the 3 terms. So I can just take common things out and I am rewriting this one as, okay, sum over r means sum over all states. Remember, it is not sum over all levels. Okay, to be very precise, it is sum over all states. Be very careful about that. Okay, so just sum over r, sum over all states, that's okay, no? 1 plus log nr, I'm taking common things, log nr, 1 plus log nr, then it was minus alpha, so I'll be putting it as plus. I'm taking every term as plus now because negative term is common for everything, plus alpha, then plus beta er, then delta nr was common for every term, minus delta nr, I have taken minus as common out, okay, and it is just modified, so that should be equal to 0, right? So this is the condition which makes log w, otherwise f as what? M maxima, right? and you know that this corresponds to, as we think, the most probable distribution. And let us call the most probable distribution set. Now, do you remember what is the most probable distribution set we have labeled? We had labeled the most probable distribution set by some star, nr star, right? So if this condition is satisfied, then this is corresponding to the most probable distribution set. So in order to identify that, I am putting nr as nr star here. Okay, nr is put as what? Nr star, because nr star corresponds to where okay, nr star corresponds to, okay, because this is already the most probable distribution set. Most probable, that was our condition. Okay, no, that's our aim. Probable distribution set. Okay, so now let me call this equation. This is some very relevant equation. Let me call this equation some, what was that? We earlier had 6, no? So let me call this one as some equation number 7, right? Now you know that so it is sum over r, some quantity into delta nr is equal to 0. How come this one equal to 0, or in what all ways it can be equal to 0? We can say that it can be equal to 0 when delta nr equal to 0. Of course, that's a very trivial solution. Okay, or it can be equal when the coefficient here is equal to 0. And you can see that this nr is arbitrary. nr is arbitrary. We didn't say that which nr and all. So since nr is arbitrary, or we can say since delta nr is arbitrary, it is true for this equation 7 is true for any nr value or any delta nr value. This equation 7 will be identically 0 if and only if it will be identically 0, means it will be 0 for every case if and only if the coefficient is equal to 0. It will be equal to 0 if and only if the coefficient is identically equal to 0. Okay, so that is our argument. That's a very valid mathematical argument. So since delta nr is arbitrary, it's very important that you just put up the arguments. Okay, you never place step on to the conclusion without putting up the necessary arguments. That's very important in a derivation. Since delta nr is arbitrary, okay, equation 7 is identically 0. If you are running short of time, of course you can just avoid it, but see that you have these conclusions is identically 0. Okay, if and only if what is that? The quantity in the bracket is identically 0. It vanishes for every nr value, right? So I can say that that's a speciality. 1 plus log nr star just means that it's a very specific value which maximizes the distribution set, or which is the most probable distribution, plus alpha plus beta er. Okay, I'm writing the quantity in the bracket, that is equal to what? 0, right? I think there is no doubt about it. So let me just rearrange this one. So I'm rewriting, that is log nr star, okay, that's equal to, on rearranging, let me take that alpha and 1 to the other side, so it will be minus 1 plus alpha, okay, minus beta er, right? You know that this alpha is a constant. Alpha is an undetermined multiplier. Alpha is treated as a constant for the time being. So 1 plus alpha will be another constant, which I can write as some log of a constant. There is nothing wrong. So which can be written as, I am writing log of some constant. Any constant can be written as log of another constant, right? Okay, any quantity can be written as a log of some other quantity. So I'm writing it, you will understand what is the benefit. Log C, that is for algebraic advantage. Okay, manipulation advantage. So minus beta er. So I'm just rewriting, because alpha 1 everything is constant and c is also a constant. That's the meaning, right? So continue now, take this log c to the other side. So it will become log nr star minus log c. It's log a minus log b, which is nothing but log a by b. So it becomes log of nr star divided by c. Log of nr star by c. So that will become equal to minus, simply minus beta er. I think you are able to understand. You can smell out where do we proceed. So if that is the case, what will be nr star? Therefore, what will be nr star? So you can get nr star will be equal to simply exponential, or e raised to minus beta er. And I think, okay, you have seen this expression somewhere before. Okay, or I can say simply that this nr star by c, it is actually nr star by c. I can multiply with the c here. So that is, okay, let me call this one as some equation number 8. So nr star is equal to c e raised to minus beta er, right? So let me keep it there. And I think you have seen e raised to minus beta er. Okay, which we have been calling as what do you say, the Boltzmann factor and all. It is coming up once again, right? Now one more thing, we are not yet finished. Our aim is to finally get an expression for PR, right? The probability, right? Don't forget about it. Now from our condition 2a, from 2a, which was one of our constraints, from 2a we had the equation. What is the equation? That n, the total number of systems in the ensemble, that was written as sum over r nr, sum over r nr. That is the constraint, first constraint to be satisfied, right? Now in the case of most probable distribution, I can write nr as nr star. Remember, nr star is a very special value of nr, okay, the set nr. So sum over all r nr star. So that happens when the distribution set is most probable distribution, right? So nr is replaced by nr star when it is ensured that the distribution is most probable one. So that's equal to nr star. Can you use equation number 8 here? So I'm using equation number 8 here. So what will happen, instead of nr star, I will be substituting c e raised to minus beta r. C is a constant, so I'm taking c outside. So c into sum over r, I'm using equation number 8 here. Okay, e raised to minus beta er, e raised to minus beta er. Let me call this one as equation number 9, right? Now let me take one thing. Therefore see what's going to happen. Okay, let me take equation number 8 by equation number 9, equation number 8 by equation number 9, because that makes some sense. You'll see that. So what is equation number 8? That is nr star. Okay, the nr star denotes corresponding to the most probable distribution, that's the only thing, divided by n. N is the total number of members in the ensemble. And what is nr or nr star? Nr or nr star was the number of states having energy er. Nr star was the number of systems out of n systems in the total systems in the ensemble, which is having what? Energy er. The very first assumptions, equation number 1, you have to refer back, please. Okay, so nr star by n, what will you be getting? You will be getting nr star is of course c and c will be getting cancelled. Can you see that? The c here and the c here will be getting cancelled because okay, that's not of any use here. So it will be what you will be getting is e raised to minus beta er from equation number 8 divided by the denominator will be getting sum over r, means sum over all states, e raised to minus beta er. And I hope that this equation is something that you can easily recall from your previous experience, and you will see that this equation is nothing but our PR itself. This is nothing but our PR itself. The probability, okay, that our given system, okay, is found in an energy state ER, right? So you can see that the ensemble method is also, or ensemble method, or otherwise you can see the method of most probable distribution, which we obtain by making use of the Lagrange's undetermined multiplier method, is also giving you finally, okay, what do you say, the probability that a given system is at a given instant of time is found in a state with a particular energy ER at a given temperature T. Okay, because it's a canonical ensemble where the system is supposed to be in thermal equilibrium at a given temperature, or it is in equilibrium with a heat bath, right? So that is the way. And once you think of why the LHS is giving you PR, because you know, okay, let me go back. See, this is our final conclusion. Anyway, we go to the go back to the beginning of our derivation. See, remember. So what was this symbols meaning? Consider a canonical ensemble of n systems sharing a total energy E. Let nr, see, this is the quantity that comes in the numerator, okay, of our final expression. Nr be the number of systems in the ensemble with energy Er at any given time T. See, out of n systems, out of total n systems in the ensemble, nr systems are assumed to be in a state with energy Er. And we wanted to get the probability that, okay, one given system is found in a state with energy Er. Certainly, won't it be depending on the representation of these systems in our ensemble? If there are more member of, okay, those microstates in our given collection of ensemble, okay, then more will be the probability that the system is found. So we can say that PR will be equal to what? NR divided by total N, because NR is the number of systems in the ensemble which is found to, which is having an energy ER, and this N is the total number of systems in the ensemble. So of course we can see that PR will be equal to NR by N, provided that NR is corresponding to the most probable distribution that the system can have. Okay, hope that it makes sense, and that's about our alternate method to derive the Maxwell's the Boltzmann's distribution, otherwise known as the Gibbs canonical distribution, or simply canonical distribution, by the method of most probable distribution. See, let me tell you one thing before we wind up the session. What actually matters is this expression. Okay, and whether you understand this expression, and the way in which you arrive at that expression is only a matter of our academic curiosity, like how come that equation. And what's more important is that it's not the process by which you reach, but then you may ask, why did you or why do we derive the same expression by two different methods? Of course it helps. Why? Because one thing is that it will help you to master some of the mathematical techniques that will be useful in later topics. For example, since you followed the method of most probable distribution to derive the same equation which you had derived earlier, you are now familiar with the technique of Lagrange's undetermined multipliers. So this technique could be understood, or this technique could be at least introduced, because we followed the second approach, right? Moreover, it tells you that instead of considering the systems, we considered an ensemble of systems. So means we were considering the canonical ensemble formalism for this particular derivation. Okay, and we have seen that whether you go by the direct method or you go by assuming our system to be a member of the canonical ensemble, finally the mathematics is so sound, the mathematics is so powerful, the method is so powerful that we will be getting the same results. Okay, that will give you a validity, that acts as a validity proof of our ensemble formalism. So it serves two purposes. But remember, we will be doing a lot of things with this equation for PR. Okay, and I think that before we move on to any other thing, we will do some problems on PR by using the denominator. Hope you still remember what is the denominator that we are having in this equation. The denominator was represented by Z. Okay, or I told you it is also represented by Q and Vt, which we called as the canonical partition function, sum over R, what is that, e raised to minus beta ER. So hope you still remember this equation. And I told you, or we confirmed, that this Z, which acts as the denominator, the normalization factor in the PR equation, is serving as the bridge between statistics and thermodynamics for a system in canonical ensemble. So now in the next topic, we will be deriving the thermodynamical quantities starting from the Z. So once you know the PR, or in turn, once you know the canonical partition function for a given system, means you know the thermodynamics of the system. And we will see in the next topic, next lecture, how do we derive other physical properties like say the pressure, or the internal energy, say the Helmholtz free energy, whatever it is, CP, CV, whatever it is, all those thermodynamic quantities, how do we derive it from starting from the knowledge of set of the given system. Okay, please read on. If you have any doubts, feel free to contact me at any time. We will discuss. Thank you.